about the stretch reflex. And so that would be monosynaptic. Okay. Would it be contralateral or ipsilateral? Ipsilateral, because the stimulus and the response are on the same side. Okay. So the tendon reflex has the exact opposite response of the stretch reflex. And remember that when we look at the tendon reflex, this does not have to do with muscle spindles, but it actually has to do with proprioreceptors located in the tendon. So receptors located in the tendon are stretched. So the response is actually, in response, the muscle relaxes. So the muscle actually lengthens. And so instead of shortening and contracting, it actually lengthens. And so sometimes when you stretch, you might sense this. So it could be like stretching, and then you think that you've stretched as much, but if you hold it for a little bit longer, this reflex will kick in, and then you'll be able to stretch the muscle even more because the muscle actually relaxes. So this actually protects the muscles and the connective tissue and the tendons from actually being ripped or torn. So it protects against the tearing of tendons and muscles. So that's the tendon reflex. And if we look at it in your book, would this be an example of polysynaptic or monosynaptic reflex? Is an interneuron present? Yeah. Yes. Okay. So this is the tendon right here of this muscle, right? And when it stretches, then what happens is that it sends a signal, and so this one, the flexor, will actually relax a little bit, and then the quadriceps will actually relax, and the whole thing will become will reduce tension. Okay. Actually, it says here that they cause this muscle to contract. So if that muscle contracts, then it goes like that, and this muscle actually lengthens. The significance of this is that your tendons do not easily stretch. Some people have more stretchy tendons than others, and so you might know of people that have hypermobility, and sometimes that actually causes a destabilization of the joint, because they can easily hyperextend their joints and cause more stretching of the tendons, and then the joints can actually sometimes pop out of place. Tendons, when you damage them, it sometimes feels like a burning sensation, so when you tear them, and they are not easily repaired because they don't have a lot of blood supply to them, so it's really hard to repair them. Maybe not as hard as cartilage, but the tendons, it takes time to repair them. And so you probably have all experienced a sprain, for example, where it takes a lot of time for that tendon to repair itself and to kind of tighten back up to help to stabilize the joints. So this is a protective one. Okay, so the next one is a combination. So it is called the flexor and then the cross extensor, and usually these go together. So flexor is when the muscle contracts in response to pain. So it just has a different stimulus, right? So the stimulus would be the nociceptors. So it's not that the muscle is being stretched that causes it to contract. It's actually that you have a sensation of pain. And so, so the receptors would be nociceptors. Okay. So a good example of this would be if you put your hand on a hot stove, right? You automatically pull it away, and that reflex is fast. It doesn't have to go to the brain to be integrated, and it helps to protect. So remember that the spinal reflexes are fast and they are protective. Okay. So we have those nociceptors. So then when we look at the cross extensor, this actually has to do, this is actually a contralateral reflex. So it's on the other side. And muscles contract to extend a limb. Bless you. So the extensor part is that we're extending either the hand or we're extending the leg. So the best example of this one is probably when you step on something that is sharp and painful. So if I step down, I am actually kind of relaxing this other leg. And so if I pull this up, I'm going to fall, right? So if I pull away, what has to happen is that this other leg has to extend, and it has to be quick in order to catch me. And so the same thing can be said for a sympathetic fight response. So for example, if somebody grabs your arm, oftentimes you'll just automatically push with the opposite arm, because that grabbing of one arm causes this cross extensor response, which would allow you to push somebody away. Okay, so if we look at these, okay, so this is the example of grabbing somebody's arm. So if somebody grabs me, or if I am in pain, so I would flex that muscle, and then notice how there's interneurons that take this stimulus across the to the other side of the body. So what then happens is that the biceps relaxes, and then the triceps contracts, and it causes me to extend my arm. So this is really important, as I mentioned, in balance. Right? So if you're falling, for example, that extensor muscle will help also catch you and keep you from falling. So those are important. So these would also be polysynaptic. Okay, so the flexor part is actually ipsilateral. The extensor part would be contralateral on the other side, and they're polysynaptic. You want to write polysynaptic down if you don't have that in your notes. Okay, so we also have superficial reflexes, which have to do with the skin. And so if you look at those patellar hammers, they generally have a weird structure on the other side of them. So they have the part that you actually hit the patella tendon with, but the other side can be used to stimulate these superficial reflexes. And so one of these examples is called the, oops, do I not have my picture? It's down below. The Babinski reflex. Okay, so actually this would be the plantar reflex. So this is on the sole of the foot, or the bottom of the foot. And you stroke the skin there in this way, from going from the heel towards the toes. And if you do that, your toes should curl in. So the normal is toes curl in. The abnormal one, which actually is normal in babies up to about the age of 1, is that they have the Babinski sign. And this is where the toes curl up, or we'll put the fan up. Right, so they extend up rather than curling. So if you were to do this, if the doctor was to do this, then it would suggest that you have damage really low down in the spinal nerves. And so generally this is between L4 and S2 damage. If it be abnormal, so let's say if they did this to me and they found that my toes go like that, they'd say, oh, well, we have some damage to that area. So normal is that your toes are going to curl inward. But if you did this to a baby, like 6 months old, they would have that, the toes would go up. There's another one that's kind of interesting that has to do with the lower abdominal. So supposedly if you touch the sides of the lower abdominal, sometimes that causes a reflexive response so that those muscles contract. And so that's another superficial reflex. And they don't really quite understand how it works, other than it is a spinal reflex that's fast and is not something that is learned. Babies also have startle reflexes, you know, or kittens do too, right? So you startle them and they go, oh, like that, right? And so that's another example of a spinal reflex.
So is the fanning of the toes like in a baby, is that the CNS or PNS not fully developed?
Yes. And so they actually think it has to do with when you're born, your nerves are not fully myelinated. And so they think it has something to do with myelination. But your textbook mentions that they don't really understand the mechanism of how it goes from that reflex to this reflex. It's kind of exactly the opposite. So it's kind of weird that you would have exactly the opposite things going on in babies versus not baby responses. Okay. So I need to go back and just mention this idea of nerve plexuses. So when we look at the ventral rami, so this is not in the dorsal rami. Oops, ventral rami. So remember that is what branches off the spinal nerve almost immediately. And this is what is going to serve the sides of the body and the fronts of the body and the limbs. So what we get are what are referred to as plexuses. And these are interlacing nerve networks. And it's kind of weird because those spinal nerves, the axons from one spinal nerve will come together, and then they'll come apart, and then they might even come together again before they go out and serve the nerves that are out in your body, like the radial nerve or the ulnar nerve or the medial nerve, so the nerve networks, when we look at them, they're in the cervical region, they're in the brachial region, and lumbar and the sacral region. So if we look at what these plexuses look like, oh, do you want me to go back? Somebody said shoot. Okay. So you're like, oh, what is this, right? It's kind of crazy. And supposedly you can palpate it. You know, I don't know if I've ever felt trying to feel for the brachial plexus, but like right here. So when you look at this, the interesting thing about this is that by the time those nerves branch off of this, is that a nerve that is going to go to one muscle. So say there's a nerve coming out, my radial nerve, and it's going to go to my triceps, and it's going to cause that muscle to contract. It is actually going to be a combination of axons from these different cervical nerves. And so what that means, if I get a damage right here because of a herniation in my C3, it is not going to completely paralyze my triceps muscle, because there's also C2, C4, and C5 that are also going to be contributing axons or fibers to that muscle. And so I'm not sure if that's why we have these, but it is just kind of a benefit of them, because it means that just by damaging one area of a one of the spinal nerves, it's not going to completely shut down the action of the muscle, okay? So I'll just write that as each muscle receives axons from multiple spinal nerves. So damage to one spinal nerve is not going to completely paralyze the muscle. So people that have herniations, like I had a herniation C5, C6, right? And, or maybe C6, C7. And then what would happen is that my triceps got really weak, right? So they test this by having you press against them, right? So that you might put your hand here and they're like, okay, push, 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 right? And they're like, oh, well, your right side is much weaker than your left side. So what that tells me is that perhaps you have nerve damage so that your tricep muscle is weaker on one side. And so generally the muscle just gets weaker. It does not become paralyzed. So if we look at that radial nerve, right? So this is my radial nerve, this green, this one that's coming out. And notice that it has fibers from C5, C6, C7, C8, right? Because of that interlacing nerve plexus. Okay, so that is it for the somatic division of the peripheral nervous system. So now we're going to talk about ANS. And what does ANS stand for? Yes, autonomic nervous system. So it is as opposed to the somatic division, right? So this is autonomic. Oh, geez. Is that their ringtone? I think I could handle that. Okay, so versus somatic. Okay, so what is the difference in the innervation? What does somatic innervate that autonomic doesn't?
It's like
Yes, not the smooth muscle. So somatic is your skeletal muscles. So those reflexes that we just talked about, those are part of the somatic division of the peripheral nervous system. So the autonomic is smooth muscle. I feel like I've written this a few times. Smooth muscle, glands, and cardiac muscle. And we'll talk about this, but we also have autonomic reflexes. So what was an example of an autonomic reflex that we looked at in lab? Not the hearing part. That wasn't a reflex. That would have been the pupillary reflex, right? So it is a fast response to light. And what it does is it causes the pupil, causes the iris, which is a smooth muscle, to constrict. And so it causes constriction. It can also cause dilation. Like, for example, if somebody comes behind you or you stroke the person's back of their neck, their eyes will constrict. So the pupillary reflex has two different parts to it. So when we look at the autonomic nervous system, we have a, instead of just having motor neurons extending out with their cell bodies in the spinal cord, the motor neurons here, so the ANS has motor neurons, right? They're going to go out to the muscles, into the glands. So these are the things that cause the response. And that's versus the sensory neurons, right? Have a 2-neuron, I'll put with neuronal chain. Okay, So this is versus somatic. In somatic, you have only one neuron extending out, right, from the spinal cord or from the brain, the axon. So there's super long cells, right? The axons for the sciatic nerve reside in my spinal cord, and they come down, and then they come out and go to my toes, right? That's a super long cell. So when we look at this, we have what are called the preganglionic neuron. That is going to have its cell body in the gray matter of the spinal cord, for example, or in the brain. And then this is going to connect to the ganglion. Right? The ganglion is that aggregation of nerve cells. And then we have the postganglionic neuron. Right, so pre versus post. So this is very different. And so we can also talk about where the ganglia are located. And I showed you that in the case of the sympathetic division, the ganglia are actually right close to the spinal cord. But in the case of the parasympathetic division, the ganglia are right close to the organs that they innervate. Okay, so we're going to talk first about the parasympathetic division. So the parasympathetic division specifically has a cranial sacral outflow. Okay, so that means that spinal nerves that are coming off, motor neurons that are coming off the middle of your back are never parasympathetic. The ones that are coming off, like the cranial nerves, we talked about how some cranial nerves are parasympathetic. Those, like the vagus nerve, those are there, and then we have some that are coming off of the sacrum. So it's just the way that it is organized, okay? So the parasympathetic division is relaxation, conservation of energy, and digestion. So in the case of the heart, it would slow the heart down, but in the case of digestion, it actually speeds up the contractions of the stomach and the intestines so that you have peristaltic contractions moving the food through the digestive tract more quickly than if it wasn't being innervated. Okay. The other thing about it is that the ganglia are located far away from the central nervous system. And so when we talk about this, we would say that the preganglionic axons are long, right? So they have these long axons that might extend like all the way to the kidney. And then you have the ganglion next to the kidney. And so then the postganglionic axons are short. Okay. Okay, so let's look at a diagram that kind of summarizes some of this. So this is somatic. This is like one of my favorite diagrams because it has so much information. So this is actually somatic. And so notice that the nerve cell body is in the central nervous system, and the axon is very long, and it goes to skeletal muscle. So this would be parasympathetic. So here we see that this preganglionic neuron is very long, and then the postganglionic neuron is very short. We can also see that there is a difference in myelination. So the autonomic nervous system tends to have lightly myelinated axons, or in this case, the axons, right, actually have no myelination. So it tends to be a little bit, the reflexes tend to be a little bit slower because they are not heavily myelinated. Okay, so this shows the cranial sacral outflow. So notice that the ganglia, the preganglionic axons are very long. Notice that the ganglia are located close to all of these organs, so that my postganglionic axon is very short. And so we can compare this to what is going on with the sympathetic nervous system. So I'll just write the sympathetic down here. Okay, this is your fight or flight. Oops, fight or flight. And this uses energy and also inhibits digestion. So in this case, the ganglia, oops, let's not talk about the ganglia first. Let's say that they have a thoracolumbar outflow. And then the ganglia are located close to the spinal cord. So what this means is preganglionic axons are short and postganglionic axons are long. Okay. So, for example, one of the things that they worry about if you have a herniation in the lumbar region is that sends signals to the bladder. And so the sympathetic nervous system actually, it's kind of interesting, it actually inhibits the voiding of urine, even though when you have, like when you're really, really scared, something happens, and I'm not sure how that works, something happens and it causes you to pee your pants. But generally, if you're just, running from somebody, or if you're going in and you have to make a presentation, right? So when I get ready to come into lecture, my fight or flight comes on, right? My sympathetic nervous system is stimulated. So generally, I do not have to go to the bathroom, and then right afterwards, I have to go to the bathroom, right? So the sympathetic nervous system usually inhibits voiding. And so if you could have incontinence if you have damage to that area of your spinal cord. And then one of the real dangers of having a herniation down really low is that it also affects the genital regions. And so that can be a problem because that could cause numbness, for example, or inhibit the ability to have an erection if you're male. So anyway, so let's look at some examples of the action of these. Okay. So let's look at the iris. And we're going to say parasympathetic and sympathetic. So what do you think the parasympathetic causes? Dilation or constriction of the iris? Constriction. How about salivary glands? We talked about how some cranial nerves innervate the salivary glands to produce saliva. If if you're in a fight or flight response, how does your mouth feel? Dry, right? And so this produces more viscous or thick. This produces watery saliva. Oops, watery saliva. Okay, how about the heart? What parasympathetic cranial nerve innervates the heart? What cranial nerve actually comes down and innervates your heart? Vagus, that's the vagus nerve, the vagabond, right? It travels outside of its origin. And so parasympathetic would tend to decrease heart. Sympathetic would increase heart rate. Okay, so bladder, this promotes voiding. So the bladder is a really interesting organ, I think, because it's smooth muscle and it will just start to contract. And when it contracts, you feel like you have to urinate, right? And then it'll contract, and then if you hold it and do not void, and that's under conscious response, then it will stop contracting and you'll be like, oh, maybe I don't have to go to the bathroom after all, right? And then all of a sudden it'll contract and you're like, oh, I do have to go to the bathroom. And so it has that kind of this contraction and relaxation response. So it's kind of interesting. So that's smooth muscle. And this promotes voiding, this inhibits voiding. So at a big job interview, generally you don't have to urinate. Digestive tract. This increases mobility. This decreases mobility. So this is why it really irritates me sometimes when you go to work meetings, right? Especially contentious meetings. Like you have to, like, you might be trying to figure out if you're faculty, then it would be like you would meet with the administration to kind of figure out how you're going to deal with certain situations. They always feed you, right? And you're like, oh, have you ever been in a meeting, a lunch meeting, and you eat, and you're like, oh, my stomach, it feels like it's just like raw food is just sitting in my stomach and nothing's happening, right? So this is why you should never eat under stressful circumstances, right? Because of that decrease in the motility, okay? So the liver is interesting because here we have an increase in glucose uptake. So that means that your blood glucose decreases. So when you're relaxed, you don't have a lot of glucose because you don't need to send it to the nervous system or to the muscles. But this actually decreases glucose uptake. So what that means is that you have an increase in blood glucose. Did that answer your question? Yeah. Okay. So this is why chronic stress can be a problem, because chronic stress can increase your glucose, which can actually lead to you becoming insulin resistant. And so it can lead to the metabolic syndrome where you gain weight, even though you haven't increased your consumption of calories. So stress can cause problems with diabetes, but it can also lead to weight gain because you're actually utilizing glucose as food. And you actually might want to eat sugary foods too. So when you're stressed out, you tend to want to eat carbohydrates, right? So that affects weight. Okay, now notice how these generally have opposite effects, but there's one response that actually has to have the sympathetic and the parasympathetic working in action. And this is with the genitalia. Okay, so males and females both have erectile tissue. So in the female, it's the clitoris. And the clitoris has a small part that is exterior, but it actually has a much larger portion of the clitoris, which is you can't see. So when we look at the genitalia, we would say that this causes erection, right? So that means that the blood flows into that tissue, the clitoris and the penis become erect. And then we also have to have ejaculation. Not ejaculation, sorry, orgasm, which would be ejaculation on the males. So we'll just put male ejaculation. Okay. So in females, it's the contraction of the vagina, and also the uterus contracts, right, during orgasm. And so the interesting thing about this is that in order to have the entire sexual response, you first have to be relaxed so the parasympathetic nervous system can take effect. And being nervous and having the fight or flight or response is going to cause erectile dysfunction. And then you have to override the parasympathetic and have the sympathetic response, which actually causes the ejaculation. So it's probably no wonder that a lot of times something goes awry and you can't have the full sexual response. So these have to be work in coordination. So I'll put I'll put work in coordination, not opposition. Okay, so there are some things that are only innervated by the sympathetic nervous system. So we call this unique innervation. So I'm just going to skip over this part, sorry. Okay, so the unique sympathetic innervation. So an example of this is blood vessels. So the parasympathetic nervous system does not tend to or does not innervate the blood vessels. So what the sympathetic nervous system does is it has what is referred to as vasomotor tone. So vaso refers to the fact that this is blood vessels, motor because it's muscle, and then tone means that it's under a constant state of partial contraction, okay? So we have blood vessels are under a constant partial state of contraction. So when a blood vessel contracts, that is called vasoconstriction. So that's contracting, that's decreasing the diameter of the blood vessel, versus vasodilation, which is increasing the diameter of the blood vessel. That's just a scribble. So it's vasoconstriction versus vasodilation. So when there's lots of action potentials being sent via the sympathetic, it causes more constriction. And then when there's just a few action potentials, it causes it to dilate. And that is actually what allows blood to be shunted to different parts of the body. So like away from your gut and towards your muscle during the fight or flight response. So the other thing would include sweat glands. Sweat glands are not innervated by the parasympathetic nervous system. And then we have the erector pili muscles. Does anybody know what those do? I think maybe there's only one P in there. Let me look it up. Does anybody remember? These are on the skin. Yes, so they make your hair stand up on end. So when you sweat and your hair, or when you get scared and your hair stands up on end, that is due to the fight or flight response. So, yeah, there's only one L, sorry. P-I-L-I. Okay. And then the other thing would include the adrenal gland. Okay. So we're going to talk about the adrenal gland after the midterm, because we were going to talk about it as an endocrine gland. But part of the adrenal gland is actually nervous tissue. And it is the adrenal, the inner part, which is called the adrenal medulla. And one of the things that the adrenal gland produces is epinephrine. And a version of epinephrine, which is also called norepinephrine. So these are released only when the sympathetic nervous system releases them. They're also not only neurotransmitters, but they're also hormones. And so, for example, if you are having vascular shock, where your blood pressure drops dramatically, maybe due to an allergy. So say you have an allergic reaction, your blood pressure just drops. They give you epinephrine, and why do they give you epinephrine? What does that do? Yes, so it increases the heart rate, it constricts blood vessels. So if you constrict the blood vessels, then the blood is shunted. So dilation would actually decrease blood pressure. So this actually increases blood pressure and then would increase heart rate, which would get the blood to where it needs to be, like to the brain. So you need to enter the heart muscle in order for survival to happen. Okay? So those things that are just innervated by the sympathetic nervous system. Okay, so we talked about anatomy. Now we're going to talk about physiology. And so when we look at the physiology, this would be how it works. And so this would be the mechanism of action. And so we have what are called cholinergic fibers. What is a fiber? Axon, right? So a fiber is an axon. Cholinergic refers to that these are the axons that release acetylcholine. So axons that release acetylcholine. And remember, they do that, they release it into the synapse. And this is I think it's abbreviated as ACH. Okay, so acetylcholine is ACH. The thing about acetylcholine is, remember that it is a direct acting, it's one of the few really important direct acting neurotransmitters, meaning that it binds directly to the ion channels and causes sodium ion channels to open and depolarization to occur. Okay, so when we look at the somatic motor neurons, are all cholinergic. Okay. In the case of this, acetylcholine is always stimulatory. So ACH is always stimulatory. When it is released in the synapse with skeletal muscle. Okay, so I'm going to put this in parentheses because this is not really ANS. So autonomic, remember, is kind of the opposite of the somatic, or it's different than the somatic, okay? But I just wanted to point out that there's cholinergic fibers there too. So we also have all of the preganglionic, so I'll put all preganglionic, spelled that wrong, gangli. So even in the sympathetic nervous system, the ones that are the neurons that are connecting to the ganglia from the central nervous system, they all release acetylcholine. The postganglionic neurons, the fibers depend. So when we look at in the parasympathetic nervous system, so we'll say postganglionic, fibers of the parasympathetic nervous system. I'll abbreviate that, parasympathetic release ACH. Okay, so does the parasympathetic always stimulate, or does sometimes it inhibit? Sometimes it inhibits. So in this particular instance, ACH can actually be excitatory or inhibitory, depending upon the organ it innervates. Okay, so I'll put can be excitatory or inhibitory, depending upon organ it innervates. So innervation is just where the fibers connect. So maybe it's innervating the pacemaker of the heart. So in this case, if it is innervating the heart, it is actually going to inhibit the pacemaker, right? And it's actually going to slow the heart rate back down. Okay? If it's innervating my salivary glands, it's going to actually cause them to secrete more, so it's excitatory. If it's if it's releasing it to my stomach, then it's going to cause contraction of the smooth muscle in my digestive system. So those are cholinergic fibers. So the other types of fibers that we have are adrenergic. Okay, what do you think Adren is a abbreviation for? Adrenaline, excellent. Okay, so adrenaline. So this means that they do not release acetylcholine. They're not cholinergic. They release norepinephrine. So they're adrenergic. And norepinephrine can be excitatory or inhibitory, right? It inhibits the bladder, right? So can be either excitatory or inhibitory. And it is only in the postganglionic axons of the sympathetic nervous system. Okay. So remember the preganglionic, all preganglionic release acetylcholine, which is excitatory, which then sends a signal to the postganglionic neuron. And then only in the sympathetic nervous system are they adrenergic, not cholinergic fibers. Now, we won't get into this today because we don't have time, but the cholinergic and the adrenergic fibers have synapses with their organs, and there's actually different types of receptors. So we'll talk about like beta blockers that can decrease heart rate, for example, because they affect the way that the heart responds to norepinephrine. So when you hear about beta blockers, it actually has something related to what we're talking about here. So I just want to show you this image again. This one image I showed at the very beginning, which has all of the really cool stuff going on in it. Oops, bypassed it. Okay. So this has all the information that we talked about, right? So ACH, acetylcholine. This is a big C, a big A, big C. Always write it out on the test. So notice ACH being released always by the preganglionic. And then notice that here it's innervating the adrenal medulla gland, which is actually thought to be a misplaced ganglion. So instead of being near the organ or being near the spinal cord, they think it's actually in this gland, it's misplaced. Maybe not, maybe that's not the best word. Okay. And then the parasympathetic, ACH. Sympathetic, NE. What does NE stand for? Norepinephrine. And then they have stimulatory or inhibitory effects depending upon the receptors that they bind to. So it looks like we'll finish up pretty soon on the next lecture, and then we'll have a little review for the midterm exam. So remember, you need to bring your questions. If you have any questions or clarification you need for that review sheet, you can ask me any questions.